pH is an incredibly important variable for physiology. It turns out it's a regulated variable. It's something that your body pays attention to, senses, and will expend a lot of energy to maintain within a certain range. So let's go through the basic principles of pH. I know this is a review for most of you, so I'll try to do this quickly. At room temperature, at 25 degrees Celsius, a solution is neutral if its pH is 7. And so what is pH? Well, it's an indication of the amount of hydrogen ion, free hydrogen ion in the solution. So if we have a solution that has a lot of free hydrogen ions, then it'll be more acidic. A solution that has fewer free hydrogen ions will be more basic or alkaline. So again, at 25 degrees Celsius, we have a pH value of 7.00, which is equivalent to 1 times 10 to the negative 7th moles per liter. And on this chart here, we can see different values. So for example, saliva is slightly acidic, urine's a bit more acidic, tomatoes and grapes, others fruits are quite acidic, cola, vinegar are extremely acidic, lemon juice even more acidic, and finally stomach acid is extremely acidic. In the other direction, you have pancreatic secretions, which are slightly alkaline, baking soda, which is alkaline, soap solutions, which are alkaline, ammonia, which is alkaline, chemical hair removers that are alkaline, and sodium hydroxide, which is extremely alkaline. So pH is temperature sensitive. So as you move away from 25 degrees Celsius, there's more, for example, if you increase the temperature, there's actually more dissociation of water, pure water, into hydrogen and hydroxide. And so actually the hydrogen ion concentration will go up slightly. So for example, at 37 degrees Celsius, which is normal core body temperature for humans, a neutral pH is actually 6.8, and that makes sense because you'd have slightly more, because of the thermal energy, you have slightly more hydrogen ion. Despite this fact, we usually just consider 7 to be neutral, even though it's slightly off for human body temperature. And the next thing is very important. The normal pH of blood in the body is about 7.4. So that's a bit alkaline. So we have homeostatic mechanisms that are critical, that critically maintain this pH around 7.4. Now, if your blood pH were to become lower than 7 or greater than 7.7, you may die. So it's extremely important that your body keep your pH within the normal range. So why exactly is pH so important? And it's, as I said, it's a regulated variable. There are chemoreceptors in the body that sense pH, and we'll talk about those more later in this class. In order to understand why pH is important, we need to understand the concept of denaturing proteins. So as we talked about earlier, proteins have a primary structure, which is based on the sequence of amino acids. And so essentially a protein is a long peptide chain, and it can denature, which means it sort of unspools. And as it does that, it goes from its normal native structure to this abnormal structure, and it would lose all biological activity. Now, in some cases where certain small proteins, if you denature them, and how can they be denatured? Well, you can have changes in temperature, you can have a strong acid or base, and organic solvents such as chloroform or alcohol. These can denature a protein. And in some cases, they're actually able to, if you take away the change that you imposed on the system, the proteins may actually be able to refold themselves. Now, this doesn't always occur, but sometimes it can occur, and that's called renaturation. And in that case, the protein would regain its normal biological activity and its normal native structure. However, in a lot of cases, when you denature a protein, it's a one-way street. They won't come back. So, for example, if you think about an egg, the egg white is clear, and it contains a lot of proteins. So there are these globular proteins, which are like the ones shown here, each with a very specific shape and so forth. And when you heat them, these globular proteins essentially unwind. And when they do that, they then interact. So you might have hydrogen bonding, van der Waals forces, ionic bonds between different protein strands. And then you essentially have a network of connected proteins. And that's exactly what happens as you cook an egg. You go from a clear state, in which you have these soluble proteins, to a state in which the proteins are no longer soluble and they're connected to each other. And they essentially push out the water also. So you have a loss of water as you cook. And so this process is called denaturation of proteins. So again, let's come back to pH. So why is pH so important? Hydrogen ions in the solution can participate in hydrogen bonding and van der Waals forces. So when you have excess free hydrogen ions, this disrupts the biomolecule's non-covalent bonds, leading to a change in the molecule's shape or conformation. So you essentially have a denaturation with a low pH or an acidic environment. Potentially, you can also do it with a high pH. An alkaline environment can also denature proteins. And an easy way to remember this is just to think of ceviche. This is a form of denatured protein that's pretty delicious. So ceviche isn't exactly raw, but it's not exactly cooked either. It's never cooked in the traditional sense. Ceviche goes through a chemical process that effectively rearranges or denatures the proteins in the fish or the shrimp. And this is much like the application of heat. So again, proteins are normally held together by bonds, non-covalent bonds, and that form the three-dimensional structure of the protein. When you add heat, or in this case acidity, it breaks down some of those bonds, and then the protein shape is lost. So in the case of ceviche, all you need is lime juice, which has a pH of about 2. This denatures the proteins, freeing up these long chains of amino acids, and then allows them to essentially rearrange and interlink, forming this sort of mesh network of protein. And this pushes the water out, so it essentially changes the protein enough that it appears to be cooked. Okay, so normal blood, it has a pH of 7.4, which is slightly alkaline. So let's think again about where these hydrogen ions come from. So as I mentioned earlier, water has a small tendency to dissociate into hydrogen and hydroxide. There are also acids in the body. For example, you have lactic acid, carbonic acid. And in the other direction, of course, you can have, if you have an excess of hydroxide ions, the OH, then you would be alkaline. And so there are also sources of hydroxide ions that occur naturally in the body. So how is the blood pH maintained relatively constant in your body? Well, you have buffers. Buffers moderate changes in pH. If an acid is added to a solution that contains bicarbonate buffer, for example, then the bicarbonate anion, which is HCO3-, binds to some of the free hydrogen ions to form carbonic acid. And so this acts as a sort of a buffer. Well, it is a buffer, and it keeps the hydrogen ion concentration from going too high and becoming damaging for the reasons we just explained. You don't want to denature your proteins. Okay, let's do a problem. So given that the normal pH is 7.4. What is the hydrogen ion concentration of blood in nanomoles per liter, nmol per liter per L? Recall that nano means 10 to the minus 9. And also, if we think about our laws of logs, recall that 10 raised to the log x equals x. And here's our equation for pH. pH equals negative log of hydrogen ion concentration. Recall that the square brackets indicate a concentration. So let's go ahead and do this. I'll do this example for you. So we have this equation, pH equals negative log of hydrogen ion concentration. We're going to plug in pH, which is the value we have. That equals negative log of H. So again, recall that 10 raised to the log x of x equals x. So now what we're going to do is multiply both sides by -1. Remember, you can always, in an equation, you can always multiply or do any manipulation as long as you do it to both sides. So we're going to multiply both sides by -1. So we have, because we're trying to figure out what the hydrogen ion concentration is. So we now have -7.4 equals log of hydrogen ion concentration. And then what we do is we simply we take both sides and we use the values on either side as the exponent. So 10 raised to the -7.4 equals 10 raised to the log of H. And recall that that's going to simply be H. So that's why we have H in brackets here. Okay, so now we have, if we do this on a calculator, we'll find out that the hydrogen ion concentration equals 3.98 times 10 to the -8 moles per liter. Recall that we want our answer to be in nanomoles, which is 10 to the -9. So then hydrogen ion concentration equals 40 times 10 to the -9 moles per liter, or 40 nanomoles per liter.